Hello, everyone. I'm going to talk about our paper, MCDNN, which is an approximation-based execution framework for the deep learning. And this is a joint work with researchers from University of Washington and Microsoft Research. So today, talking about wearable computing, most of people will think of these low data rate sensing devices such as Fitbit. This is because they enable many widespread applications, and most of them just measure the body motion, just like what a pedometer app does. So, however, people now are adding more high data rate sensors, like cameras, to the wearables. So looking into the future of the wearable computing, the applications are required to process more data at real time, which puts more pressure on the system resources. So in this paper, we're investigating what kind of infrastructure is required to support the camera-based wearable devices. But before I go into details of this problem, I'll first give you a few tastes of what kind of applications that we can enable. So after we combine computer vision with camera-based wearables, we can think of many useful applications for both consumers that you and I can use every day, and for the enterprise that can be used at workplace. So for example, like at consumer side, if your cameras can see what you do, a bunch of magical things can happen. For example, it can tell you where you left your keys. On the other hand, in the manufacturing, studies show that more than 80% of failures come from human. So if the wearable cameras can be used to monitor human errors, it can give us real-time help and prevent these mistakes from happening. Very similarly, police officers now carry body cameras during the patrol. However, these videos are simply recorded and to prevent anything bad happen. But if we can identify wanted persons and license plates at real time from the video stream, these body cameras can be much more useful. So in summary, there are a whole bunch of possibilities that we can do with the camera-based wearables with computer vision. But people may ask, does the computer vision really work for the real world? So in recent years, deep learning became the revolutionary technique that changed the computer vision. This figure shows the accuracy of object recognition has been increasing rapidly after we used the deep learning. And now machines are almost as good as humans at object recognition. But although the deep learning makes the computer vision more accurate, they're also known to be compute intensive. This table shows one of the best recognition models for face, scene, and object recognition. And notice that this model requires 1 to 40 giga floating operations to execute. What's worse is that this is the computation for only one single frame. So if we apply the deep learning to a video stream at 1 to 30 frames per second, so the workload can be up to 1.2 trillion flops per second. So do we really have enough resources to run the deep learning for a mobile execution environment? So let me give you more details about the resource usage. In a typical end-to-end mobile system, it consists of a mobile device component and a cloud component. In the mobile device, it has an imager that takes in the video stream, and a processor that can perform some computation, and a radio for the communication with the cloud. And for the heavy workload, the computation can be also offloaded to the cloud. So now let's take a look at the workload. Suppose the frame rate of input video stream is 10 frames per second, and each frame requires 30 gigaflops for recognition. So therefore, the total computation demand is 300 gigaflops per second. On the other hand, looking at the budgets we have, the battery capacity of a typical mobile device is 10 watt-hours. And our target for this new application, suppose is 30% of the total capacity and running for 10 hours for a day. So therefore, we can sustain 300 milliwatts as our power budget. On the cloud side, our targeted cost is $10 per person per year. And based on the energy consumption on the mobile device and the computation costs in the cloud, we translate these budgets to the compute power that can be achieved. And in fact, we can get at most 9 gigaflops per second on a mobile device, and 48 gigaflops in the cloud based on GPU or CPU instance. And compared to the workload, we found that there's 2 orders of magnitude gap between the deep learning workload and our budgets, no matter you run this on the mobile device or in the cloud or combine them all. So our goal in this paper is to bridge this gap to make the deep learning work for the mobile system. How can we do that? At this point, we have to learn how deep learning works. So the deep learning, also known as the deep neural network. This figure shows an example of a neural network. A neural network can be viewed as a data flow graph, where each node or layer performs some array processing operations. And look inside each layer. So these operations are mostly matrix multiplications. And researchers have been working on reducing the computation and memory costs of neural networks. And since they are matrix multiplications, there are standard methods to compress them. So first, for example, we can apply SVD to the matrices and use low-rank approximation to reduce the size of matrices and the total computation. Second, we can sparsify these matrices by zeroing very small values and use low bit width floating numbers. Third, we can directly modify the architecture of the entire neural network model and reduce the number of layers and the size of the weight matrices. So these approaches can substantially reduce the resource use of neural networks, but they also have different effects in terms of the trade-off between accuracy and different resources. So in this paper, what we did in essence is managing the trade-off between the approximation and resource use. And more specifically, we did the following three things. First, we have a detailed categorization of the trade-off between approximation and resource use for many optimization. And second, we find two new optimization for this streaming multi-application settings to achieve better accuracy and resource use trade-off. Third, we need to select a right approximate version of these models during the runtime and our budgets. We formulate this problem as approximate model scheduling, and we come up with a heuristic solution to it. So next, let me first give a flavor of what detailed categorization of these trade-offs. So let's first focus on the memory and accuracy trade-off. In this figure, the x-axis is the accuracy, and the y-axis is the memory in log scale. And in this graph, we show one unoptimized model for face, scene, and object recognition. And after we apply these approximation approaches we mentioned before, we generated 10 to 60 approximate models for each task. And here I only list a subset of data points. The takeaway from this graph is that we can substantially reduce the memory use with gradual accuracy loss. And next, let's focus on the energy and accuracy trade-off. The x-axis in this graph is still the accuracy, and the y-axis is the energy. And we measured these all the approximate models on the NVIDIA Jetson board. The bottom two horizontal line shows the energy consumption if transmitting an image to the cloud through Wi-Fi or LTE. And the third line shows the energy budget that is allowed to compute for each request. But note that this energy budget is computed statically. And during the runtime, this value will vary according to the workload. And therefore, we can categorize these models into three classes. First, for these smallest models, we should always execute them locally because transmission costs more energy. A subset of models can be executed locally under the energy budget. And there are also certain large models that exceed the energy budget when execute them locally. So for these models, we should probably offload them to the cloud. We also have a cloud cost and accuracy trade-off, but due to time limit, I won't talk about it. You can find it in our paper. So okay, previously I've been talking about existing optimization on the neural networks. Next, I'm going to talk about the new optimization for streaming multi-application settings. So there are the specialization and the model sharing. And in this talk, I will only talk about the specialization. So the specialization is about exploiting the temporal context in the video stream. So consider performing a face recognition to a video. A standard deep neural network model can recognize 4,000 faces. However, in the video, most of faces within a few minutes come from a small subset of classes. So for example, if I have a meeting with my colleagues, for a certain period of time, I will mostly see only 3 persons. So therefore, the specialization is about to produce more compact models for the skewed classes in the video context. So to utilize the specialization, we devise the following runtime system. And by default, we will use the full model to serve all the requests. And once the system detects a temporal context in the video stream, it will generate a compact model specialized for these skewed classes. And after that, in most cases, it will use this compact model for recognition. However, when the compact model predicts the input as outside of these skewed classes, the system will fall back to use the full model. So now let's take a look at the resource and accuracy trade-off for the specialization. So I pick one compact model for each task showed before and compare them with the full model in accuracy. Typically, a compact model loses accuracy when compared to the full model if applying them to the same general distribution. However, in fact, we only need to use compact models for these skewed classes. And when these compact models are used to recognize only 7 classes, their accuracy are even higher than the full model. And then looking at the energy consumption of these models, the compact model consumes 1 to 2 order of magnitude less energy than the full model. So let me show you a video demo when we apply the specialization to recognize actors in the video. So on the left side, it uses the full model without specialization, while on the right side, it uses specialization. And at the bottom, we show the accuracy and frame rate per second. And we can see that if using the full model, the frame rate is only about 14 frames per second. However, the specialization can quickly detect the temporal context in the video stream and generates a compact model specialized for these skewed classes to reduce the latency while still maintaining the accuracy. And after that, the frame rate increases to 24 frames per second. And our runtime system can also detect the context change and use back to the full model when the context changes. And overall, the specialization can achieve higher accuracy and frame rate. Okay, next, I'm going to talk about the scheduling problem that decides which approximate model to use during the runtime. So before I explain the details, let me walk you through some simple examples. Suppose we have 2 recognition tasks, and for each task, we have 2 models. One is the full model, which has higher accuracy and requires more resources. The other is the approximate compact model, which is less accurate and also consumes less resources. And looking at the model 1, for example, its accuracy is 90%, and it requires 8 units of memory, 2 units of energy if executed on a mobile device, and 2 units of cost if executed in the cloud. We also have certain budgets and constraints for our system. On a mobile device, the energy budget is 14, and the memory capacity is 10. And in the cloud, the cost budget is 14. And our goal is to maximize the overall accuracy throughout all the requests. So let's first focus on the energy and cost budgets. So we may receive many requests for either task 1 or task 2. For each task, we can choose to either use the full model for higher accuracy or use the compact model for lower resource use. And we can also choose to run it on the mobile device or in the cloud. But over all the time, we have a higher bound for the total energy consumption and costs. So therefore, we can frame this problem as a packing problem. But what's interesting here is like usually there are only one place to pack models, but here we have 2. And on the other hand, let's focus on the memory constraints. So suppose at this time point, we've already loaded model 4 in the memory of the devices. And at this time point, the device loses the internet connection. So all the subsequent requests must be executed on a mobile device. However, when it receives a request for task 1, we found that the device doesn't have enough memory for even a compact model, model 2. So therefore, we need to evict the cache model from the memory to serve this request. And in fact, we are facing the paging problem here for the memory constraints. So in essence, in summary, the approximate model scheduling is a joint packing and paging problem. For the packing problem, over all the time, we need to pick versions that satisfy the energy and cost budgets. While at each time step, we need to also pick versions that fit in the device memory. And our goal is to maximize the accuracy. For each single problem, we know there's an optimal algorithm to solve that. But for this joint problem, there's no known optimal online algorithms. So therefore, we come up with a heuristic solution. And there are three key points to our algorithm. First, we need to estimate the future resource use and compute the budget for each request and pick the model with the highest accuracy. And second, we need to account for the paging cost to reduce the oscillation of switching models in and out on the mobile device. And third, we increasingly use more accurate versions when a model is more heavily used to maximize the accuracy. Okay, next, to evaluate our system, we perform a trace-driven experiment. We generated some synthetic connectivity trace on the mobile device, shown in the bottom panel. And then we applied the workload of the face analysis, including the face, gender, age, and race recognition. We also run the scene recognition as a second application. We compared MCDNN to two Strawman strategies, which only uses the device or use the cloud. And we can see that if we only use this device, it will run out of the battery budgets before 10 hours. And if we only use the cloud, requests are not served when the device doesn't have the internet connection. And in comparison, MCDNN can achieve good accuracy over all the time and makes trade-off necessary to sustain throughout the day. So in summary, MCDNN has a static compiler which generates approximate models and carefully categorizes them during the development time. The runtime consists of a device and cloud runtime. The device runtime receives requests from multiple applications running on the mobile device. And a heuristic scheduler selects an approximate model and executes it either on the mobile device or in the cloud based on the remaining energy and cost budget. MCDNN also has a runtime optimization, such as specialization, to exploit the temporal context in the video stream. And in conclusion, MCDNN makes efficient trade-off between the resource use and accuracy. We formulate the approximate model scheduling problem and come up with a heuristic algorithm. And third, we also design a generic approximation-based execution framework for the continuous mobile vision problem. Thank you very much, and I can now take questions.